The comparison test can be used to determine if an infinite series AN converges by comparing it against another series Bn whose convergence is known. So for example, the geometric and harmonic P series, which are typically used to compare against in this test. And if all the terms in series A are smaller than or equal to all the terms in series B, for all n greater than some integer, and Bn converges, then An also converges. So really have to think about this. And in contrast, if all the terms in series A are greater than or equal to all the terms in series B, for some n greater than n, and the series Bn diverges, then the series A also diverges. And we'll apply this to practice problems. The limit comparison test is particularly useful for a series A, where An is a rational function of n. And again, we compare this infinite series against an infinite series whose convergence is already known, like the geometric and harmonic P series, which are typical. Now, given these two series have all positive terms, for all n greater than some positive integer, and Bn is not equal to 0 because we can't divide by 0, we have three rules in a limit comparison test. And these take some getting used to by applying them to different examples. So if the ratio of An and Bn as n approaches infinity is equal to a positive number, then both series An and Bn converge or diverge. And for the second rule, if the limit of An on Bn as n approaches infinity is equal to 0, and Bn converges, then An also converges. And if the limit of An on Bn as n approaches infinity is unbounded, and Bn diverges, then An also diverges. And we'll get some practice in applying this test to get the hang of it. Determine if the following series converges using the comparison test. So as n becomes very large, this term will dominate, and we can compare this series with a series that we already know. So that's going to be the harmonic P series, and we can take the constants outside the series, so this can be written as follows. And this here is a harmonic P series with the exponent P greater than 1. So we know that this series converges. And if we designate these terms in the series as An, then we can see that these terms here are always going to be smaller than Bn for all n. So therefore, due to this condition, and because our series here converges, then this series also converges by the comparison test. Let's determine if the following series converges using the limit comparison test. And this test is good to use when we have a rational polynomial. Now for a large n, the n cubed term will dominate in the denominator, so we can choose the following series to compare against. So we have 3n on n cubed, which is 3 on n squared. And now we take the limit as n approaches infinity of the ratio of both terms in both series. And now we can see the 3's cancel, and the n squared goes in the numerator. So we get the following expression. and this evaluates to a limit of 1. So because we've got a positive number, so then rule 1 of this test applies, meaning that both series either converge or diverge. So if we check this series over here, and just take the constant outside, well, as we can see, this is a harmonic P series with the exponent greater than 1. So we know that this series converges, and therefore both series converge by the limit comparison test.